In this section, we'll use all of the material that we learned in sections 7.1 through 7.4 to solve exponential and logarithmic equations and also to solve application problems. So the first thing, I want to go over a summary of those properties. The first is that x equals base a to the power y, and log base a of x equals y. Those are equivalent equations, okay? And that means that we can convert between the two, saying log base answer equals exponent is the same as base to the exponent power is equal to the answer. All right, the other thing that we'll use is that exponential functions and logarithmic functions undo each other in the sense that they're inverses. So if you have a function a to the x and you apply the logarithm base a to that expression, then the logarithm and the exponential undo each other and you're just left with x. Same thing, if you have log base a of x, if you apply the exponential base a, then the exponential and the logarithm will undo each other and you'll just end up with x. Also, don't forget that the log of a product is the sum, this should be a plus, is the sum of the logs. And also a log of a quotient is the difference of the logs. And x to the r, if you're taking something, raising it to a power and taking the log of that, that's like taking that power r times the logarithm. All right, so let's use all of those properties to solve some exponential equations. So here I have 3 to the power 2 minus 5x equals 11. The first way I'll solve this is to translate to a logarithm equation. So base 3 to the power 2 minus 5x equals answer 11. So I can convert that to a log base 3 of 11 equals 2 minus 5x. All right. So then at this point, I got the variable x out of the exponent. Now it's on like this base level, and I can just solve for x like normal. Notice that this log base 3 of 11, it's just a number. It's like, the number 7 or something. So I'm just going to treat it like a number. So I'll just subtract 2 from both sides. So log base 3 of 11, whatever that is, minus 2 equals negative 5x. And then divide both sides by negative 5. I get log base 3 of 11 minus 2 over negative 5. That's what I get for x. All right, now what you can do is suppose you want a decimal approximation for this number. I'm going to use the change of base formula to rewrite log base 3 of 11 so that using the natural log, I'll say natural log of 11 divided by natural log of 3. That's the same thing as log base 3 of 11. So this is the change of base formula, COB. And then whatever that is, minus 2 divided by negative 5. And now that's something that I can plug into my calculator and get a decimal approximation for. All right. So if I did in parentheses, the whole numerator in parentheses, natural log of 11 over natural log of 3 minus 2 all over negative 5. So I get approximately negative 0.03. Let's say negative 0.037. Okay, so that's method 1. Just by translating the exponential equation into a logarithm equation. Method 2, we can apply the logarithm to both sides. Now, what we can do, if you're applying the logarithm to both sides, you can apply log base 3 to both sides, or you can apply the natural logarithm to both sides. It doesn't really matter. Maybe I'll do both. So if I had 3 to the power 2 minus 5x equals, I'm going to leave some space here, 11. If I applied log base 3 to this side, and then log base 3 to this side, what I get is that log base 3 of the exponential base 3, those guys undo each other, and we're left with 2 minus 5x equals log base 3 of 11. And then you can solve it. We're at the same step here. You can just solve it the way you did here. And subtract 2 from both sides. And divide by negative 5. So that's one method. Apply log base 3 to both sides to undo the exponential base 3. But you'll notice it also works if you just apply the natural log to both sides. If I did natural log of 3 to the 2 minus 5x equals natural log of 11. If I do that, then I'll use this property that says the log of something raised to a power is equal to that power times the log. So this power here, this is like the r, can come out front like as a multiple. So this will be 2 minus 5x times natural log of 3 equals natural log of 11. Okay, natural log of 3, natural log of 11, those are just numbers. So let me divide them both sides by natural log of 3 so I can get the x by itself. Now I have 2 minus 5x equals natural log of 11 over natural log of 3. Subtract 2 from both sides. And then last but not least, divide both sides by negative 5. So again, natural log of 11 over natural log of 3 minus 2 all over negative 5. Okay, so you'll see that in any case, I got the same answer. It depends on what method is the most convenient to you at the moment. Okay, let's look at another example. In this next example, there's really only going to be one method that makes sense, okay? Let's solve 5 to the 3x minus 1 equals 2 to the x plus 3. And of course, using our elementary methods, we'd like to make it so that both the sides have the same base. But that's not possible here without using logarithms. So what I'm going to do is I'll apply the natural log to both sides, sort of like I did in this last method here. So I'll say natural log of 5 to the 3x minus 1 is equal to natural log of 2 to the x plus 3. And when we do that, the exponent comes down for both of these expressions. And I'll have to make sure to put things in parentheses. I got 3x minus 1 times the natural log of 5 equals x plus 3 times the natural log of 2. All right, now it's not going to be as easy as this problem because I only had an x on one side of the equation here. In this example, I have x's on both sides of the equation. So here's what I'm going to do. I'm going to break up these parentheses by multiplying this natural log of 5, which is just a number. I'll multiply it, distribute it into the parentheses here. And this natural log of 2, I'll distribute that into the parentheses as well. That'll open up those parentheses for me. So, first term, I've got 3 natural log of 5 minus natural log of 5 equals, 3x. Sorry, I forgot my x. 3x times natural log of 5. Let me put the x out front. Doesn't really matter. Equals x natural log of 2 plus 3 natural log of 2. This problem is going to feel a little awkward just because the natural log of 2, you're not used to manipulating that around like any other number, like a whole number, say, but it is just like any other number. And we're going to move it around and manipulate this expression just like we would as if it were a more familiar number, say. All right, next thing we're going to do is notice I have a term involving an x here and a term involving an x there. I'm going to move these two terms to one side and everything else to the other. So I'll add natural log of 5, so I can get rid of that. And I'll subtract this term, minus x ln of 2. So those go away. Now, unfortunately, I can't combine these terms. They're not like terms. So I've got x times 3 ln of 5 minus x times ln of 2, and that's going to equal 3 ln of 2 plus natural log of 5. Okay, now this last step, now that I have the two terms involving x together on one side, I'm going to factor out that x. So it'll be x times 3 natural log of 5 minus natural log of 2. And my last step will be to divide both sides by this number, 3 natural log of 5 minus natural log of 2, to leave x by itself. So what I get now is x equals 3 natural log of 2 plus natural log of 5 all over 3 natural log of 5 minus natural log of 2. So it doesn't seem like you're done, right? Because, again, it just doesn't feel like a nice, friendly number. But I assure you, if I plug this into my calculator, I'll get a number out. So let's go ahead and do that together. I'll use parentheses around the whole numerator. 3 natural log of 2 plus natural log of 5, so that's my numerator. I put the whole thing in parentheses, divided by 3 natural log of 5 minus natural log of 2. Oh, shoot, I forgot to use my parentheses at the end there. I'm pretty confident that that's correct, but I am going to retype it in just to be sure, making sure I have parentheses around the entire denominator. Okay, so x is approximately, let's give it 4 decimal places, 0.8920. The next digit is a 7, so that'll bump it up to a 1. All right, let's just go through the procedure one more time. If you have an exponential equation, you can either translate it, if possible, to try and get x by itself, translate it to a logarithm equation, or you can apply a logarithm to both sides. You can apply log base, whatever base number you're using in the equation, or you can apply any other base. You can apply log base e, which is a natural log. There are some problems where it's going to be really difficult to choose a base to apply, in which case just use the natural log or log base 10, something like that.